So our basic definition of flux was for a uniform electric field, so its strength and its direction was not varying over the surface. However, we've had many electric fields that are in fact not uniform. They vary in strength and or direction. So we need to think about what that's going to mean for our flux. And here, what might be obvious or intuitive to you is that we need to move into an integral. And so there have been many cases in physics and mechanics where there's one form, which is an integration form, which you need to do if something isn't constant, but it simplifies to multiplication if you do have something constant. So the same thing is going to happen for flux. In the vast majority of situations that we talk about in intro-level electricity and magnetism, we will be able to do multiplication rather than needing to do the integral because we can simplify. However, it is important to understand that the integral is really our starting point. And depending on what your situation is, you may be able to partially simplify, but not fully simplify. So what's going on with this? We imagine that we have a surface and we break it into little tiny areas, dA. So this is just a tiny differential piece of the area, and they've gotten different subscripts to denote, hey, there's two different pieces. Now, at our different pieces, we have different electric field vectors. Now, right now, we're not worrying about what's causing the electric field or anything like that. We're just considering the fact that our two electric field vectors are not the same at this point and that point. So if you were to say, well, let's just multiply them. I don't want to do an integral. Well, which value would you use? Would you use this value of the electric field or that value of the electric field? Clearly, you can't multiply if something's varying. So we can think about some little amount of flux coming from this piece, which would be then the area vector for that piece and your electric field vector at that piece dot producted, and then you integrate. So effectively, we're going to have lots and lots and lots of little pieces, kind of try to calculate the flux, or at least set up the flux at every single piece, and then integrate. So what that ends up looking like notationally is that we have E dot dA, and dA here is just talking about that differential little piece of area. Now E here, notice that if we're doing an integral, this isn't constant, and so one of the ways we can write that is that it is a function of position, where position is, say, over your surface, maybe we have X and Y, right? And we're going to get into complicated three-dimensional shapes as well. So I'm going to call this E as a function of R, where R then just means position on surface. Okay? So recognize that I'm showing you kind of the more complicated setup, but I want to make sure that you understand that E here can vary. Why is it varying? It's varying with position. So that's kind of why I would use this more complicated notation here. And then we integrate over the surface. Now, this is again a very general form. So this equation is just telling you in general what's going on. For any given situation, you would need to make it more specific. So in the case that we have a surface that lies in the xy plane, you would integrate, for instance, from x min to x max, and then y min to y max. You have E as a function of x and y, and again it's a vector and it's dotted with dA, where notice that in this case up is now the z hat direction. So that's actually kind of a little bit easier than when we go to do the dot product. But your dA then would basically be dx dy, and then you have your little z hat direction here. And so what that means is when we go to do the dot product, you would only take the z component. This is all really complicated. We're never going to actually, I say never, we are rarely going to need to do this. This is not what our work is going to look like. But recognize that that kind of is what this means. So your surface integral, we are normally not going to need to do out. But if you needed to do it for a square like this, you would just do a two-dimensional integral over both x and y. You're going to see some notation in this class that's coming from multivariable calculus. I know that you haven't had I know that most of you haven't had multivariable calculus. The book knows that you haven't necessarily had multivariable calculus. So please don't panic when you see something new that doesn't necessarily make sense to you. The book is going to explain it, and I'm going to do my best to explain it. And in most cases, we're going to be able to simplify it away. Let's look at one possible simplification here. And so in this case, I'm going to say that over our surface, the magnitude of our electric field vector is constant, but the angle is going to vary. So when we go to do this dot product, cosine theta appears. And now your position vector, again, that just means, for instance, over x, y of your surface, or whatever plane your surface lies in. Later, we're going to get to curvy surfaces that make this more complicated. You have the strength of your electric field vector, which we said, hey, that's constant. So this is where a simplification is going to come. But now theta is varying. So what we need to do then is we can actually pull out our electric field strength because it's constant, but then we're left with this function, cosine of theta, where theta is, for instance, a function of x and y of some sort, and we would need to know what that function is. But then you can just integrate it. And I say again, just integrate it, where maybe you have an integral over x and maybe you have an integral over y. So this would be kind of the complicated form. Now notice, for instance, if both e and theta are constant and this pulls out, if theta pulled out, which it doesn't necessarily, in this case if it's varying, we can think about what's left behind, which is just that you have your integral over dA of your surface. That equals A, right? If we imagine our surface and every little piece, you're adding them up, that just eventually gives you A. So this is really key. If you've never thought about a surface integral before, be aware that that dA is just a little tiny area, and if you added up all of the little tiny areas of our surface, we would of course get the area. Again, you can't do it in a situation like this where there's still something else inside the integral, but if you've pulled everything out, this is pretty simple. So we'll look at some more examples, and again, in general, we're going to only deal with problems in this class where we get to simplify this a lot.